Changes of state. Whenever a material changes state, its temperature doesn't change because the kinetic energy of its particles doesn't change. So all the energy that's transferred to or from the material is used to melt or freeze, condense, or vaporize the material, changing the potential energy of the particles. Because remember, thermal energy of a material is the total of all the kinetic energy and potential energy of the particles in the material. The energy that's needed to change the state of 1 kilogram of a certain material is called latent heat. And here's a formula that shows us the latent heat of fusion. So that's equal to the heat energy required to change the state of the material divided by the material's mass, the sample's mass. So LF is the latent heat of fusion, and latent heat of fusion is measured in joules per kilogram. EH is the amount of energy required to melt or freeze a sample of mass m of that material. And we see something similar for what we call latent heat of vaporization. So this is for changing from liquid to gas or from gas to liquid. So LV is the latent heat of vaporization, again measured in joules per kilogram for that material. And EH is the amount of energy required to vaporize or condense the sample of mass m. Let's try an example. How much energy is required to melt 12 kilograms of lead? So we'll use our latent heat of fusion formula. We know the latent heat of fusion for lead is 2.3 times 10 to the 4 joules per kilogram. And the heat energy is our unknown. And we know the mass of the sample is 12 kilograms. So we substitute in, our units are correct. And so we get the heat necessary is 2.76 times 10 to the 5 joules, or 276,000 joules of energy to get that done. All right, let's try this one. How much energy is required to completely vaporize 5 kilograms of ice initially at a temperature of minus 20 degrees Celsius? This one will require a few steps because we have to change temperature and change a couple of states. So step one, we're going to warm the ice to change its temperature. So we'll use our heat energy equation with changing temperature, mc delta T. So the mass is 5 kilograms. C, the specific heat capacity for ice, is 2,100 joules per kilogram degrees Celsius. And there's our change in temperature, 0 minus negative 20 degrees Celsius. So here we have our heat required when we work that out is 2.1 times 10 to the 5 joules, which is 210,000 joules of energy. Now we have to melt the ice, so we know the temperature won't change in this step. So we use our latent heat of fusion formula, similar to what we did earlier. Here's our latent heat of fusion for water, and our unknown is the heat energy required. So we get 1.65 times 10 to the 6 joules, or 1.65 megajoules. Now that we've melted the ice, we're going to warm the liquid water to change its temperature. So we'll use our temperature equation again, but now you'll notice that the specific heat capacity is for liquid water, which is different from the specific heat capacity for solid water, or ice. So now it's 4,180 joules per kilogram degrees Celsius. And we get just over 2 megajoules for that job. Now we're going to vaporize the liquid water, changing it from liquid into gas. So we use our latent heat of fusion formula. And we'll substitute in the latent heat of fusion for water. So there's the latent heat of fusion for water in joules per kilogram. Our mass is still 5 kilograms. There's the mass. So we'll solve for the heat required. And so we need 1.15 times 10 to the 7 joules of energy for that to vaporize the water, or 11.5 megajoules. So the total, now we have to add up the values that we calculated in all of these steps. So when we put them all together, the total heat energy required is 1.55 times 10 to the 7 joules, or 15.5 megajoules, 15.5 million joules. So that's a lot of energy to change the ice into water vapor. And that's latent heat and changes of state.